Welcome to this explainer. Today, we're taking the seemingly abstract, kind of intimidating magic of computer programming, and we're going to turn it into a highly visual, completely solvable mystery. Even if you write code every single day, slowing down to see exactly how a machine processes information at the micro level, it absolutely changes how you debug and build things in the digital world. So, let's get into it. So, how do you see what code is actually thinking? A computer executes instructions in literal milliseconds, right? It makes it seem like pure magic. But what if we could slow time down? What if we could pause the machine and basically spy on exactly what the computer is thinking at any given microsecond? Well, that is exactly what computational thinking allows us to do. We're going to become digital detectives today, dissecting the hidden logic behind the software we use every day. Here is our roadmap for this investigation. First up, tracking invisible variables. Then, mastering the trace table. Third, organizing data with arrays. Fourth, navigating 2D grids. And finally, number 5, debugging logic traps. Okay, section 1, tracking the invisible variables. Every great investigation has to start with the smallest pieces of evidence, right? And in coding, those are our variables. Think of them as dynamic little containers holding the numbers, text, and data that drive our entire program forward. Now, looking at this, notice how the visual flowchart logic on the left maps directly to the written pseudocode on the right. It's like a translation. The flowchart, with all its arrows and decision diamonds, acts as a literal map of the path the data is about to take. Meanwhile, the pseudocode gives us the structured text version. Together, they give us this amazing bird's-eye view of how variables like X, Y, and Z will interact, calculate, and loop long before a single line of actual code is ever written down. Moving right along to section 2, mastering the trace table. Knowing the path is one thing, but to truly track our variables as they run through complex loops, we need a computational magnifying glass. Enter the trace table. A trace table is a structured tool used to help you trace the changing values of different variables during code execution. It effectively forces the code to slow down. It lets us record exactly how each variable transforms line by line, step by step. It basically takes the guesswork entirely out of the equation. Now, what's really interesting here is how this reveals the hidden, real-time movement of our variables as a loop repeats itself. Look closely at the columns. We've got I for our loop iteration alongside X, Y, and our final output. Before the loop even starts, X sits at 2 and Y is at 3. But the very moment the loop body executes, when I equals 1, boom, everything shifts. X jumps up to 5, and Y becomes 2. Let's watch this matrix unfold. As we step through the loop from I equals 1 all the way down to 6, try to guess the next value before we reveal it. Ready? By step 2, X is 7 and Y is 5. By step 3, X swells to 12 and Y to 7. And by the time we hit our final iteration at step 6, X has skyrocketed all the way to 50 and Y has grown to 31. Without this table, that rapid-fire math is completely invisible to us. But with it, we have a perfect chronological footprint of our program's behavior. Which brings us to section 3, organizing data with arrays. So when you're tracking, say, 100 different users, relying on individual variables is just going to create chaos. We absolutely need a system to organize our evidence at scale. That's where a data structure, specifically an array, comes in. An array is a format to organize data for easy use, using an index to find target array items. Instead of having scattered messy variables everywhere, it keeps related items locked safely together, using a numerical index so you can instantly pinpoint exactly the element you need. It really helps to think of an array as a row of connected storage boxes. Take this array, for example. It's named age, and it has a size of 10. Each box holds a specific item. But the absolutely crucial part here is the number sitting below each box. That is our array index. If we want the first age, which is 8, we just look at index 1. If we want the last age, 25, we look at index 10. It is a perfectly organized filing system where every single piece of data has an exact numbered address. Okay, let's see how this data actually talks to itself when we introduce some instructions. Looking at the pseudocode on the left, we first assign the number 16 into array index 3. Next, we want to assign a new value to index 9, and the rule says to take whatever value is in index 3 and add 1 to it. Since we know index 3 holds 16, adding 1 gives us 17. And the outcome on the right perfectly captures that result. See how the logic just flows across the structure? It's really elegant. Now for section 4, navigating two-dimensional grids.
Now, digital evidence isn't always a single straight line. Sometimes we have to expand our search into the second dimension. And the cool thing is, these abstract mathematical grids map perfectly to structures you already know and love. We have a two-dimensional array consisting of rows and columns, giving us specific coordinates, like row 0, column 1. Think about familiar games like tic-tac-toe or Minesweeper. They are built exactly on this logic. Every X, every O, or every hidden mine is really just a piece of data stored securely within a precise row and column.
Finally, let's look at Section 5, debugging common logic traps. When your code breaks, I promise you, it is rarely a ghost in the machine. It's almost always a flaw in our logic. These are the classic traps you need to watch out for. First up, wrong relational operators. Using greater than instead of greater than or equal to can completely throw off your boundary. Second, beware of always true conditions. For instance, if you write a condition that says mark is greater than or equal to 50 or mark is less than or equal to 100, well, that covers literally every number. Congratulations, you just passed everyone. You actually meant and in that case. And lastly, be really careful mixing up pre-test and post-test loops, like evaluating conditions before a user even inputs their data. It happens more often than you'd think. Mastering these skills, from plotting flowchart paths and tracking variables on trace tables to organizing data in 2D arrays and debugging those pesky logical traps, it really gives you absolute control over the machine. You've learned how to see exactly what the code is thinking, which leaves just one final mystery for you to solve today. Now that you can see the invisible matrix of logic, what kind of digital world will you build next? Thanks so much for joining me on this explainer.